guys. Welcome to our unit on nuclear chemistry. When we're talking about nuclear chemistry, we are talking about the chemistry of the nucleus. So today we're going to be talking about radioactivity, radioactive particles. So we've been talking a lot about isotopes lately, and we see in this unit two different types: stable isotopes and radioisotopes. Now, stable isotopes are those that will remain unchanged forever. So they exist in nature and they won't ever change. Whereas radioisotopes are unstable, which means they are going to change. We call these also radioactive isotopes. The way that they're going to change is that they're going to undergo radioactive decay. What happens in radioactive decay is you have unstable nuclei, and they lose energy by giving off these radiation particles that we're going to talk about. They will decay until they become stable. They will decay and decay and decay sometimes, multiple times, until they finally reach stability. And all of this with our radioisotopes happens spontaneously in nature, right? We have some kinds of radiation that we can actually induce in a lab. The ones that we're going to talk about right now happen naturally. These are natural radiation. And something to note when we're writing nuclear equations is that all of these types of radiation particles are products in a nuclear reaction. Now remember, with chemical reactions, right, according to the law of conservation of mass, in a chemical reaction, mass cannot be created nor destroyed. That's not true of nuclear reactions, all right? So in nuclear reactions, we will see that mass can be changed. So our first type of radiation, of natural radiation, is an alpha particle, or alpha decay. An alpha particle in alpha decay is a helium nucleus, and we represent it by writing 4/2 He. Remember, this is our isotope notation. 4 is the mass number of helium, 2 is the atomic number of helium, and He is a chemical symbol. We can also write this 4/2 alpha. This is the Greek symbol for alpha. It's kind of like the forwards Jesus fish. The penetrating power of an alpha particle, it's the most ionizing of all types of radiation, which means it's actually going to be the most dangerous for like human tissues and cells. Even though it's most ionizing and dangerous, it's the least penetrating because it's so large and slow moving that it doesn't penetrate. It doesn't penetrate very well, which means it could be stopped by a piece of paper. Something that thin can stop an alpha particle. If we look at beta decay, our beta particle is really an electron. Since an electron has no mass, we write the mass number as 0 and the -1 charge, right? So -1 E for electron. So this is our electron. We can also write it 0/-1 beta, and this is the Greek symbol for beta. Beta radiation, or particles, are also ionizing, all right? Just not as ionizing as alpha. But because they're smaller and faster moving than alpha particles, they have greater penetrating power. So they would go right through the paper. They could be stopped by aluminum foil or thin pieces of wood. Our last particle is gamma radiation. Gamma is very high energy electromagnetic radiation, very high energy, and it usually accompanies the decay of alpha and beta particles. Now, gamma radiation has no mass, right, and it has no protons. So we write it 0/0 gamma. This is a Greek symbol for gamma. Gamma is the least ionizing of all three types, but it's the most penetrating because it's so high energy. It will go right through the paper, the wood, the aluminum foil. It could finally be stopped by thick pieces of concrete or cement. Right? So these are all of our natural radiations. We also see some lab-induced type of radiation that we can make happen in a lab. Those are electron capture and positron emission. So for electron capture, it's the same as a beta particle, an electron. The only difference is it's in the reactants instead of the products. Remember, all of these natural occurring ones are in the products. Electron capture, an electron is captured in the reactants. So we see 0/-1 E in the reactants. Positron emission has the particle for positron has the same mass, but opposite charge of an electron. All right, so still a mass of 0, but instead of -1, we have a +1 E, right? So it looks the same exact as the electron, except with the positive sign instead of negative. This, just like the natural types of radiation, is in the products. Now, we see that we can actually write balance nuclear equations for these processes that we just talked about. All right, so when we're doing this, the goal of balancing these equations is we're going to have, usually, a nuclei that we're starting with. In this case, uranium-238 is our nucleus. So we have uranium-238. It's going to undergo alpha decay. So it's going to emit a 4,2He particle, a helium nucleus. When that happens, often you're going to have to figure out what is this other nucleus that's now produced. To balance these, you need to make sure that the mass numbers on both sides that you see in green are balanced, that they're the same. If I have a mass number of 238 over here, I should have a mass total of 238 on the right side of the equation in my products. 4 plus 234, 238. Same thing with atomic number. My atomic number 92, I need to have the same number of protons in the in the products as I have in the reactants. So 2 plus 90, 92, and if so they're the same. If I look at atomic number 90, that is thorium on the periodic table. What you see here for alpha is that our mass from the original nuclei to the new nucleus is the mass number has decreased by 4. The atomic number from the original to the new nucleus has decreased by 2. That will always happen with alpha decay. Now in beta decay, right, now we're going to actually have to figure out what is the new nucleus that's formed. If I have a mass number of 14 on the reactant side, I need a mass number of 14 on the products. 0 plus 14 gives me 14. If I have an atomic number of 6 on the reactants, I need 6 total protons, right? Atomic number of 6 on the right. 7 plus a negative 1, that's what will give me 6, all right? So I'm going to look on the periodic table for atomic number 7 and see that it is nitrogen. So I'll throw an N in there for nitrogen. In beta decay, our mass remains unchanged. Notice that we go from 14 to 14. Mass is unchanged. The atomic number here has gone from 6 to 7, all right? So it's increased by 1. Now in electron capture, remember these next two are lab-induced. We start with 5928 nickel. Now, electron is captured. That means an electron is going to be in our reactants. So we're going to have 0, negative 1e in our reactants here. We're going to do the same thing for balancing. We need the mass numbers on the left to equal the mass number on the right. So we have 59 for our mass number in the products. We need the atomic numbers to be equal on both sides. So 28 minus 1 and the reactants gives me 27 in the products. And my new nucleus that's formed is cobalt. So I put a CO for cobalt. Now, what we see here, the mass number again did not change, 59 to 59. My atomic number went from 28 to 27. So the atomic number decreased by 1. We're going to see that exact same trend in positron emission. All right, so if we have 8 over 5b boron, in positron emission, we're now giving off a positron particle, which is positive. So 0 plus 1e will be our positron particle. And we need to figure out what new nucleus is formed. 8 on the left, 0 plus 8 on the right for my mass, 5 for my atomic number on the right, or on the left. So we're going to have 4, because 4 plus 1 gives us 5 in the products. If you look on the periodic table at atomic number 4, you'll see that it is beryllium.
Oh, do you want to say how?
That had the same trend, sorry to move this, that had the same trend again as the electron capture. So the mass numbers remained unchanged. Atomic number here went from 5 to 4, so it decreased by 1. My bad.
Okay. So, now that you know how to balance a nuclear equation and you know the different types of nuclear decay, we're going to talk about how you can predict that nuclear decay. So, using our ratio of neutrons to protons, we can actually predict what sort of decay a nuclei will undergo. So if we first use our neutron to proton ratio to determine whether or not our nuclei are unstable. And if they are unstable, then we can also use that to predict what type of decay they will undergo. So our guidelines for predicting stability are right over here on the actual left side. That got kind of erased. You want to fix that for me? Thank you. Are over there. But essentially what we're going to start out with is if our atomic number is between 1 and 20 or equal to 1 and 20, okay? So elements 1 to 20, we can predict if the nucleus is going to be stable or unstable, and then if it's unstable, which sort of decay it will undergo. So if our neutron to proton ratio, which is just equal to our number of neutrons divided by our number of protons, is equal to 1, then our nuclei are stable and they will undergo no decay. But if our neutron to proton ratio is greater than 1, our nuclei are not stable, and our nuclei will undergo beta decay. And if our neutron to proton ratio is less than 1, then our nuclei are unstable and they will undergo electron capture. Now, if you think about what you just learned related to beta decay and electron capture, you can think about how this sort of decay happens because there are too many neutrons in that nucleus. Too many neutrons. So after the beta decay, our neutron to proton ratio is closer to 1 because our atomic number increases by 1. Whereas with electron capture, we have too many protons. And after a nucleus undergoes electron capture, it decays into something that has a greater atomic number, meaning there are more protons. So a lower atomic number, meaning that the proton to neutron ratio is going to get closer to 1 and become more stable. Now, if our atomic number is between 21 and 83, we actually cannot predict whether or not any given nucleus is unstable, and therefore can't predict what type of decay it will undergo. But in the future, we are going to be looking at an app on our iPads that allow us to investigate all the radionucleotides within that range. Now, if our atomic number is greater than or equal to 84, our nucleus is just really, really massive, and it's so big that it is actually going to undergo alpha decay. And it's going to undergo alpha decay because it's too big, and that is the easiest way and the only way to actually lose mass, right? If you think about how our mass number actually only changes when we undergo alpha decay. So that is why that is going to happen.
We're actually going to change this. Sorry, wrote it wrong. This is greater than or equal to 83. Up here, 82.
Okay.
Perfect.
Okie doke. So, our band of, I just really quickly want to talk about, can you guys see this? Yeah. Our band of stability. And the band of stability is a region where all our stable nuclei will fall when we're plotting number of neutrons versus number of protons on a graph. So I know this is kind of small, but on our x-axis we have number of protons, and over here we have our number of neutrons. And our band of stability would be right down the middle, and it's where all of our stable nuclei fall. Now, anything between 1 and 20 to the left of the band of stability has too many neutrons and will undergo beta decay. Anything on the right side of the band of stability, 1 through 20, is going to undergo electron capture because there's too many protons. And then up here you can see this is our alpha decay, just too big a nucleus.
And here's where we can't predict.
And this is the area where we can't predict. Exactly. So we're going to go over some examples right now of how we actually would use this and what we're going to ask you to do as practice in class. So first we have an isotope of magnesium, magnesium 28. If we write that isotope notation, that's the easiest way to figure out the neutron to proton ratio. So 28 minus 12 is 16. That's our number of neutrons. And then 12, our atomic number, is always our number of protons. You actually have to put that into your calculator and get this, which would be 1.3. Greater than 1, we're in between 1 and 20, so we're good. This is going to undergo beta decay. And then our equation would look something like this. We start out with magnesium. It's going to undergo beta decay. And it will decay into, that's a 0, aluminum, if you look on the periodic table. We'll do this example in class together. We suggest that you go ahead and try it right now on your own, and then we'll do it when we get to class and give you the answer. But all you got to do is calculate that neutron to proton ratio and think if we're in between 1 and 20 or we're greater than 83. Thanks for listening.
Thank you.
Bye.